Hello. What do you think is the relationship between the circumference of your thumb, your wrist, and your neck? Is there one? Is it the same for everybody? Well, there's an old rule of thumb, literally, that provides an answer, and it says that twice around your thumb is once around your wrist. So let's give that a try. So my thumb is about maybe 6.5, 7 centimeters around. And my wrist is about, it's like about 18 centimeters. So double 7 is 14. So that formula is in the ballpark, but not real close. If I want to try around my neck, I get somewhere around 40. So double 18 is 36. So that's not too far from 40. So we're within 10%, 10, 15% maybe. So what about you? You can try it out yourself, see if you get similar numbers or not. But what this has to do with our section today is the idea of proportionality. Is that if that rule of thumb is true, then it's saying that our wrist circumference is proportional to our thumb circumference. And our neck circumference is proportional to our wrist circumference, and the proportionality constant is about 2. So let's try to define this a little more carefully. So proportionality is basically going to be a linear relationship. And here's the definition. So we say that y and x are proportional. And we're going to denote that by this symbol. Kind of looks like part of an infinity sign. So y is proportional to x if y equals k times x and k is not equal to 0. So it's a linear relationship where the y-intercept is 0, which is an important detail. Now, there's a few facts that are useful to keep in mind when we're using proportionality. And that's, first of all, if y is proportional to x, then x is proportional to y. Second, if y is proportional to x and z is proportional to y, then z is proportional to x, a transitive property. And then one that's particularly helpful is that we don't have to restrict ourselves to linear situations, is we can talk about y equaling some constant times a function of x. So if that's true for some non-zero constant, then y is proportional to f of x. So those are a few facts. In the exercise, you get a chance to prove those, but let's focus on some examples to make sure we understand the idea of proportionality. So what would be an example of a true proportionality? And that would be the cost to buy gas. So we'll call that y versus the amount purchased. And we'll call that x. And notice, if you think about, if you go to the gas station, and so here I have number of gallons on the x-axis, and then here is my dollars, the amount I pay at the end. It's going to be a perfectly straight line, no matter whether you buy 1 gallon or 20 gallons, let's say. It's going to be a perfectly straight line where that slope is just the price per gallon. All right. So that is, so in other words, that's our k. So y equals k times x, where that slope, that k, is the price per gallon. So we don't need mathematical modeling in this situation. This is just a regular algebraic relationship. Where the modeling comes in, where proportionality is helpful, is for situations where the relationship is not perfect. So an example of that might be the amount of gas used So that'll be our y in this case, versus number of miles driven. And that'll be x. All right, and maybe this is, say, in a month. Could be in a day, in a month, in a year. But a little longer will illustrate our point a little better, because what we're doing here is we're recognizing that the number of miles is going to affect the amount of gas used, because we don't always get a perfectly constant MPGs for a car. So here's what I mean by that. If I've gotten 0 miles, I'm going to use 0 gas. Assuming I'm not just letting the car running, actually. So we start the car and we start driving. Let's say we do a lot of in-town driving at first. Then our MPGs are going to be lower, so we're going to use maybe quite a bit of gallons and not go very far. But if we get on the highway and get a better MPG, then in that case, we're going to get a little better gas mileage, so we'll use fewer gallons. All right, so let's say this is at 50 miles and this is at 100 miles, and so forth. And so back and forth, you might get a graph that looks like this. And if I try to draw a line that goes through it, notice not all dots are going to fall in that line, because some days I'm getting better gas mileage than others. But this slope is going to be the somewhere in the neighborhood of the average miles per gallon of the vehicle. Now notice, in a precise technical understanding of the word proportional, this is not a proportional relationship, because y equals kx does not predict perfectly these dots. But from an assumption point of view, it's a great assumption, because the dots fit pretty closely. And in math modeling, we usually have a messy situation where perfection is not expected, and so this is okay. And we can still use an intercept of 0 for our relationship. So we still have y equals kx in this problem. Let's try another situation, though. What if we have the cost to own and operate a vehicle versus the number of miles driven? So this is a little bit different than the last situation, because now we have more variables involved. So keep in mind, cost to own and operate, that certainly includes the cost of gas, but it also includes fixed costs. For instance, insurance, taxes, etc. So what might that look like? That's going to depend a little bit on the number of miles driven. And let's just say, again, to keep this reasonable, let's say in a month. And there's maybe 2 scenarios. Let's think about a scenario where the fixed cost, let's say, is about $80 per month. And we'll compare a situation where maybe we're doing 200 miles a month versus 2,000 miles. Well, notice in the 200 miles situation, that $80 is going to be a big chunk of our expense for the month. Because if we only go 200 miles, depends on our MPGs, of course, but if we get 40 miles to the gallon, that's only five gallons. If we get 20, then that would be 10 gallons. So we're going to get a picture that looks, maybe it's somewhere between 100 and 120. So we may be getting a graph that looks like this. And notice proportionality, we can't have an intercept, so a proportionality assumption of this is not close at all. So this is not proportional. All right. On the other hand, what if we're going 2,000 miles? So now notice that $80 is going to be a lot less of our overall expense for the month. Because now at 20 miles to the gallon, now we're doing 100 gallons, that could be another $300. And so now we're getting a picture that might look something more like this. And so proportionality is a lot closer. Now, it's still not perfect, but the question we have to ask ourselves, is this an acceptable approximation that makes our problem solving, our mathematical modeling simpler? And so we might say something to the effect that this is an approximately proportional relationship, just like our example before was. So y is approximately equal to kx, and maybe for our purposes, we can use that slope to make predictions and carry on in whatever way our model is needed. So this gives you the basics of what proportionality is. It pops up in a lot of different areas, so it's a really helpful tool when we're doing the defining the problem stage to make an assumption of proportionality, because it gives us a starting point. But we'll see it in action in a more careful example in the next video. So we'll see you there.